Okay, so let's proceed with what we started last time, and then I think we should be having some fun as well today with some numerical examples that will demonstrate some main features of our solution approaches. So last time we started looking at the torsion of a circular cylinder. It is important that this cross-section is circular. If it's not, strange things will happen, which we will eventually also look at towards the end of the course. But presently we have a cylinder, it's fixed at one end, there is no body force or force per unit volume, there is no acceleration. So it's a sort of a quasi-static thing. I'm going to twist the end. I'm just going to look at the solution for a given angle of twist, which could be a rotation through beta. That would be angle in radians. Or I could have a torque applied at the end, which was T. Okay, so that or the other one, it doesn't matter. The solution proceeds pretty much in the same way. And essentially what we did was we started with a proposal for the displacement. Now that proposal for the displacement took the following form. We argued that we do not expect in a cylindrical coordinate system any radial or axial displacement. These are intrinsically motivated by our understanding of the problem from our first mechanics course, right? Which assumes isotropy. So if it's not isotropic, other things might happen. But presently, it's zero. And what we expect is a radial displacement. And then we argued that that radial displacement, tangential displacement, will increase with the distance away from the axis of the cylinder. So it depends on r. And also, this end is fixed. As I move towards that end, it will move more and more, so there will be some dependence on the axial position as well. So that was our argument. So that is the starting point, U. And then we calculated the strain. So in this case, we have our usual equations, gradient U plus gradient U transpose divided by 2, which gives us this strain. That's easy. Once we have this expression, which is a critical part, then the remaining mathematics, it's fairly straightforward. And then we calculated, based on the strain, the stress. And that is based on isotropic linear elasticity. That is also fairly straightforward. In this example, epsilon B was 0. And finally, we close the loop, let's say, by invoking equilibrium. And in this particular case, because the force per unit volume is 0 and there is no acceleration, the equilibrium equation simply says that divergence of the stress should be 0. Okay? So we plugged in, we came to that point, and we closed the loop, and we got a, let's say, a nasty equation because it was a PDE. And at that point, we said, well, let me sort of follow a line of attack where I say that this S is represented through a separable solution. Okay, and that is invoked by saying that it's a function of R alone times a function of Z alone. Okay, and then with that, we got two independent ordinary differential equations, both of them linear, both of them homogeneous, both of them second order, but the one for U was with non-constant coefficients, the one for V was constant coefficients. And that one was fairly easier to work with. And what we obtained was that we argued that the only plausible solution we got from that second one was a solution of the form a constant A times axial position. Okay? And then, finally, from U, we also argued that the only plausible solution was a constant. We called it at that point C1. There was a C2, but we knocked it off. C1 times radial position. Okay? So that's where we are. That's where we left last time. Okay? So now let's proceed from that point. Okay? So we have U theta. It's our separable solution, RZ, which is equal to UR times VZ, right? And that is equal to C1 times R times Z. So now I'm combining the constants and the variables. So that's AC1. Well, actually, let's do the following. Let me call this C1 times A. It was supposed to be C1R times AZ, right? So I have C1A times RZ. These are both constants, okay? So it doesn't matter what their individual values are. The whole thing as a constant matters. And let me call that a constant alpha. Okay? I'm interested in the final multiplication of those two constants. Okay? So my solution is u theta is alpha r z, where alpha is a constant to be determined. I already used some boundary conditions such as the displacement vanishing at the fixed end, in particular to argue the specific forms that I got there. But I have more boundary conditions, namely on the loaded end, to still make use of to determine that alpha. So let me remind you some of the major quantities that we have calculated. For instance, we had strain r theta, which was s comma r minus s over r. Okay? And due to the separable nature of the solution, it's u prime over u over r times v. Okay? U prime, it is C1 minus C1R over R, C1, 0. Okay? So epsilon R theta is 0. Okay? And indeed, that is something that we would like to obtain eventually from our solution, because that's what we learned in undergraduate, the first mechanics course, where we eventually argued that there was only one strain, and it was a shear strain, and it had to do with the plane with normal z in the direction theta. Okay? The plane with normal z, right, in the direction theta. So eventually that will have to do with the traction or the shear stress distribution on that surface, on the plane with normal z in the direction theta. So that's s comma z, basically. So that has a simple expression. And that's nothing but 1/2 u v prime. And so it's equal to 1/2 alpha r. Let me just quickly check up on something. Right? So 1/2 there as well. Okay. So u v prime, v was a constant times z, so now v prime is just a constant. So, and those two constants in u and v are merged into alpha. So that's what we have. Now, since epsilon r theta is equal to 0, sigma r theta is equal to 0, and sigma z theta is simply 2 mu times that, which is mu times alpha times r. So shear stress on the plane with normal z in the direction of theta. Okay? So sigma z theta would be, for instance, at that point, that, right? So it causes eventually this twisting torque, for instance, or the torque that you need to twist it through an angle beta. Okay. So we need to find out what alpha is now. And we have two, essentially, conditions. Let me go back to this board. So we can consider two different boundary conditions. The first one is when we have an end rotation, and it is a given. And that end rotation could be through an angle beta. Okay? So then we know that, well, first of all, u theta, okay, so if the end rotation is through an angle beta, the amount of displacement is that rotation angle times the distance from the axis. So it's r times beta would be the amount of angular displacement. So it's beta r is what we expect at z equals L, for instance. That is our boundary. Now, on the other hand, we know that U theta has this form. It is alpha times R times Z. And if I plug in Z equals L, I will get alpha RL. And that should be equal to, eventually, that expression. These two things are the same. And hence, I obtain that alpha is equal to beta over L. So beta is the end twist. L is the length. So this is sometimes referred to as twist per unit length, which is a quantity eventually. I will try to even use the same notation, a quantity that will pop up later on as well. Okay. So alpha is twist per unit length. Okay, so pretty much nothing should be surprising. We are just verifying our expectations through a problem that we already know, but through an entirely different solution approach. Now, that was the first possible boundary condition. The second possible boundary condition is to apply a torque at the end. Okay? Now, this part is a little bit tricky, and this part is going to come up again in the next problem that I'm going to work with. So there's an end torque, okay? Which means that if we go back to this picture, and now I erase it, okay? So in fact, let us concentrate only on the situation where there's a torque, okay? So that's the picture that we have. What that means is that whatever I apply, in other words, however I apply this torque, it might be through some strange distribution, complicated distribution of tangential stresses, or sigma, in this case, z theta. Okay? So sigma z theta could be very nicely distributed according to the theoretical equation, which is a constant times distance from r. What that would mean is that sigma r theta is linearly distributed. If it's so beautifully distributed, it is our understanding of a pure torque. Okay? On the other hand, it might be that it is not distributed like that, because this is something I am imposing at the end as a boundary condition. It might be that due to the way I'm applying the load, there is, for instance, some tangential stress there. There is nothing there, and there are more tangential stresses, sigma z thetas there. Why? Perhaps because the way I apply this torque is through some apparatus that I attach. Okay? There is some apparatus at the end, okay? And I hold this apparatus, the red disk, and I rotate that disk, and I apply the torque on that red disk. The red disk contacts the black cylinder only in a certain region. That's where the traction will be, or the stresses will be transmitted to the cylinder. Okay? So the nature of the stress distribution where the red disk contacts the surface of the cylinder, the distribution of the stress could be quite complicated. Okay? But really, in the end, we will not care, and that's the point we are trying to make. We will not care how exactly that distribution is given. What matters is that that distribution is statically equivalent to a torque. Okay? And that, eventually, you might remember, is a feature of what we called Seminoles Principle. Okay? So the point is, we do not care, and we do not know how exactly, right? And that's perhaps the key word. We don't know exactly T is applied, but the point is we do not, let's say, care, okay, at this point. We don't care. So what we will do is we will only enforce that the stresses that we obtain are statically equivalent to the end condition. All right. And this is eventually something that lies at the heart of Menance Principle, which we actually had also made use of at the very, very beginning, or we mentioned at the very beginning of our Mechanics and Materials course, the first one. And we intrinsically made use of that principle all throughout that course as well. Okay. So what that means is that I have some stress distribution at the end, okay? Sigma z theta, okay? Now, the stress times the incremental area is an incremental force. If I multiply it by the distance from the axis, that will give me an incremental moment. And if I integrate, it will give me a net moment about the axis or the torque. So now I say that that should be equal to the torque that is applied. That is static equivalence. I don't really care in principle how exactly sigma z theta is distributed. What matters is that this equality holds. Okay? So when we talk about static equivalence, that's what we mean. But now, of course, we know that sigma z theta is not anything. According to my solution, sigma z theta must be mu alpha times r. Okay? That's what I found out. And also, of course, in a cylindrical coordinate system, dA is nothing but 2 pi r dr. Okay? And so I have this thing is equal to mu alpha, in fact, 2 pi r cubed dr, r to the fourth over 4, and the integration domain is 0 to the radius of the cylinder, which we called c. And so we have the result equal to alpha mu pi c4 over 2. Okay? And pi c4 over 2 is, of course, nothing but the polar moment of inertia, or J, as we called it, okay, in our undergraduate mechanics course again. So we have T is equal to alpha mu J. That is the outcome of all of this analysis. So T is equal to alpha mu J, or alpha is equal to T over mu J. And there you go. We found out the unknown constant. So for a given torque, and for this cross-sectional geometry, which is represented with the polar moment of inertia, and for this shear modulus, that it should be the value of the unknown constant. Okay. So now, if you like, we can go back to this equation, sigma z theta. And now I know what alpha is, and I can plug in the value of alpha, which is T over mu J. The mu's cancel, so I have TR over J. Right? And sigma z theta maximum is equal to TC over J. And that TC over J will probably immediately ring a bell because it's an equation that you used many, many times in our first mechanics course. Okay. So there you go. So what we did is certainly consistent with what we did before in our earlier course. There, the approach was purely geometrical. In this case, we followed a more mathematical approach, but this allowed us to first make sense or make more clear sense of what we're doing, because we have some expectations based on a problem that we have solved before, and we are warming up to the methods that we are eventually going to use again and again. Okay? And of course, you also see some of the typical difficulties that we are facing. So it's not really easy to follow this approach, but eventually, based on this approach, we're going to be able to solve problems that we could not have solved with the geometrical approach of our first mechanics course. So it has certainly some advantages. Questions? Okay, so now what I'd like to do is now move on to a second problem. Now, that second problem, in some sense, it is simpler than that one. And it certainly is the simplest possible mechanics problem we could look at. And you will be surprised that, or you might think, why are we making our life difficult by reattacking a problem that was supposed to be very simple and now we have to solve differential equations for? But there are some points to make, okay? So that problem is, of course, tension of a circular cylinder now, okay? Torsion was, in fact, more complicated, but let's look at tension. It's going to take shorter to solve, but still there are some good lessons to be learned from that as well. Now, as simple as that problem might look, you will see immediately how extremely complicated it could actually be. So let's proceed. So this case is a tension of a circular cylinder. Okay, so I'll draw my picture again. It is the same picture. It has the same boundary conditions. So at the left end, the displacement is prescribed to 0, all components of it, at z equals 0. And there is no body force. There is no acceleration. Okay? Same picture so far as in the previous case. This is our axial direction. And eventually, we will be able to impose, or we are interested in two types of boundary conditions. We could either impose a force, let's call it P, or we could put a n displacement, which is delta. And the length of the cylinder, it's, again, L. Okay. So our solution diagram remains the same. Okay? We're going to start with displacement. And then we're going to go to strain, stress, close the loop with equilibrium. Okay? So let's start with the displacement. It is a displacement-based approach, right? That's what we are talking about in the past two courses. So displacement, it's u. And of course, again, it's a cylindrical coordinate system. We have a ur, u theta, uz. And it's a good practice always to write down all the possible dependence on all coordinates. That's what we have. And so okay, so what can we knock out? What shall I knock out? U theta. Okay, again, this is something that is based on my understanding of the problem from undergrad mechanics, right? It's an isotropic material, so I'm not saying that. Goes without saying. That's the only case we're dealing with in this course. So I pull on it. I do not expect any rotation. So this is gone. Okay. So then there is rotational symmetry. So for any position, my particular for any given cross-section, my particular radial position, for a given particular radial position, for any theta, the solution should be the same. So I do not expect any dependence on theta either, okay, just like last time. So those are also gone. Anything else? what does our undergraduate solution say? You're still an undergrad, but I always, right, I refer to your second year course. So what does the solution say from our mechanics course? Huh? Right, so now that's a little bit tricky. So what does not depend on R? Good. So it's going to extend by a certain amount. We expect these sections, right, to just get sort of translated, right? So the amount of displacement in that direction doesn't really depend on the radial position is our expectation, right? But I will cross it out, but let me cross it out carefully, okay, like that. How about UR? What does UR mean, right? So you look at the cylinder from the front with radial displacement. What should happen to the cross section? When I pull, should it get smaller or larger? You are assuming that the Poisson ratio is positive, which is plausible again. It could be negative. So if it's negative, it expands. If it's positive, it contracts, right? Does that amount of contraction depend on where I am along the cross section? It shouldn't, okay? But just like that, I want to cross out carefully, okay? Now, the reason I'm crossing out those two terms is, again, something that has to do with eventually the Menance Principle. So the reality is, when we look at the solution of that problem, so be careful. I completely constrained all the displacement at the left hand. So, and I will show you now also a numerical solution of the problem. And you don't really need a solution. You can imagine that since the left end is fixed, and let's say this is the, let me make this a little bit neater. Okay, so this is the original, let's say, side view of the cylinder. And now I'm going to pull. When I pull, the cross-section will try to contract if the Poisson ratio is positive. That's what we're assuming. And it will elongate. But the contraction is constrained on the left-hand side, right? So the reality is that the solution will look, and I'm, of course, grossly exaggerating, but just to make the point, the solution is going to look like this. So that was the original length, L. And if displacement is imposed, this is delta, right? And this is our axial position, Z. So the radial displacement is 0 there, and for sure it is non-zero there. Okay? So radial displacement, in fact, will depend on Z. And also, if you look at the displacement in that direction, due to the strange transition, actually, and we will see that this is so, the amount of displacement in the Z direction will, in general, also depend on the R coordinate. This is perhaps easier to see than that one. But this is actually also there. Okay? Now, the tricky point is that given the cylinder, the region where this complicated transition occurs, and let me shade that region, and let's call it a certain length, L. This L is under suitable conditions, which typically means that for a given radius, the cylinder is sufficiently long. If that is the case, this transition region is so small compared to the total length of the cylinder, so that we are going to omit that part. Okay? And I'm not going to see this complication. I'm going to only see that part, which is the basis of our simplification on the left-hand side. So the picture that I'm going to see is, this is the original configuration, and that's the final configuration. Okay. So you think of this left support as some sort of a frictionless support. It's a strange frictionless support because it's not like I'm pushing on the cylinder. So if I were to push on the cylinder, frictionless means that the cylinder is able to expand on that surface freely, and it's not constrained like this. So that's what I'm trying to say, but I'm actually pulling on it. So it's like a magnet almost, right? So you can apply a tension, right? But still, it can freely move in the tangential direction. Okay? So it's like a frictionless magnet, if you like. This type of a boundary condition we are also going to invoke in upcoming problems. But really, this is not a physical boundary condition. The physical boundary condition was there. We are simplifying that problem to a setting that we can actually deal with. Okay? Another way to argue this picture is to say that this picture is not a simplification of that problem. This is the picture that I see when I am sufficiently far from the end. Okay? I'm not modifying the problem. I'm just ignoring a small portion of it. And I see that picture, if you like. Okay? So eventually, the solution that we will obtain is valid sufficiently far from z equals 0. And sufficiently far, in this case, for instance, simply means that z is greater than that representative length L. In that case, my simplification, the blue simplifications, will certainly hold. OK, so now we are in good shape. Let me now take a break and demonstrate this aspect of the problem. It is worth talking about a little bit. And I'd like to do that with a numerical example. OK, so we're going to use COMSOL. That's a software that you know how to use, again, from your courses. And I'm going to look at two examples. The first one is to demonstrate the Seminoles Principle, okay, this end effect, the complication that occurs at z equals 0. And that's the problem that we have. So now the point is pretty straightforward. Okay? So it's not a small deformation problem. So the length is 1, and I'm imposing a force such that the strain is 10%. So 10% is not too large, but for elasticity, perhaps it is a bit too large. But anyway, so what you see is that the end is completely constrained. It's not friction. It's not a frictionless magnet, let me say. But now the radius is 0.1, and the length is 1, so it's 10 times more. But you see that it doesn't even have to be 10 times more, right? It's hard to hide it because it's projecting on my hand, right? But if you don't see this part, the solution is pretty uniform. What you're looking at is sigma z, okay? So we expect in this problem the stress, the normal stress, to be uniformly distributed on the cross section, okay? So if you look sufficiently far from the end, then that's the picture you see, but not near the end. So what happens near the end is, as we have discussed, so let's zoom in. So first of all, actually, perhaps you can also see the contraction, right? So this is the original radius, and it contracts a little bit due to the Poisson effect. And then, if I zoom onto the end, there is no radial displacement at this point because it's constrained. And then there's some radial displacement. And then after a while, that radial displacement becomes a constant. So in other words, if you look in this region, the radial displacement, the difference between that line and the blue line, is a constant. Okay? And that's what we are eventually going to argue. There is no dependence on z. Okay? Now, what happens if, right, if I go to the geometry, okay, and instead of having a length of 1, I put 0.1. Okay? And I recompute the solution. Just need to wait for a few seconds. And essentially what we are going to see is that, of course, there will again be an end effect. But now remember, the condition that we are sort of arguing is that the length we can move far away from the end, and still there is a considerable portion of the cylinder remaining. So in other words, when I don't see this part, the remaining part is of considerable length, so that my solution now makes sense. My simplification makes sense. However, now when you look, and just to make it a little bit more clear, let's have a perfect side view here. Now, if you look in this case, right, so what you have is that there is a decay, right? And this may not be the full position, so let's see, right? So there is a decay, right? And this is the end. So maybe it's a little bit hard to see, but for instance, here there's still some angle, which means there's some z dependence. It barely approaches a limit. So it's really hard to say that my solution is valid in this region. Okay? So even if I omit this highly red end, right, which is where the sigma z, the normal stress varies very rapidly, and I concentrate only in the blue region where the stress appears to be more or less uniform, the displacement is, for sure, doesn't look the way it did before. So I am not able to move sufficiently far from the end. Perhaps the stresses that I eventually obtain are not too bad, but the solution, the representation through this is not perfect. You see that it is already pretty good, which means a ratio of length over radius of 1 is already close to a limit, but if I make it larger, let's say 10, it's a perfect approximation. Okay? So this approximation depends on a number of things, not only the load, but also on the geometry. Okay? But eventually, it will make sense. Now, one last question. If you were to look at that picture, maybe the previous one was a little bit better, and you look at how this thing decays towards a limit, what kind of a function would you use to represent that? Huh? Exactly, some sort of an inverse exponential, right? And indeed, there is an analytical solution that is able to capture this end effect for this particular problem, and the end effects, so-called end effects, are captured through an exponential solution. So even this problem can be solved. It is hard to solve it, but eventually we will not need it. It's not because it's very hard, but because we can do away with this complication fairly easily. So let's move on to the second example. And in this example, I'd like to sort of address this assumption. So in the previous torsion example, we torqued and we say that there is no axial displacement. In this case, we are pulling and we are saying that there is no tangential displacement. All of these have to do with our understanding of isotropy. But if things are not isotropic, then that's not what happens. And here's an example I'd like to demonstrate that with. So I like this example. So when we talk about anisotropy, it's something that pertains to the material behavior. So the type of isotropy I'm going to show here is not exactly a material isotropy. It's more of a structural anisotropy. And what I mean is the following. Again, I have a cylinder, and I'm going to pull on it. Okay? Nothing too exciting, apparently. But here I have a small trick. And the trick is that I put a helix in the cylinder. The cylinder itself, the matrix, let's say, is of a certain Young's modulus. The helix is much stiffer, 1,000 times stiffer. So actually, there are schemes, for instance, with which, or production methods, to make a hull, a cylinder with a hollow inside, for instance, more resistant against torquing, you wound a fiber material around it in some fashion. That's what I'm trying to represent. So this thing perhaps would be stiffer against torsion because there is a very stiff torsional structure inside it. But I'm not going to torque it. I'm going to pull on it. Okay? Now, this helix, there are two ways to put a helix. It can be, it's called the chirality, just like a DNA. It can be right-handed or left-handed. In this case, it's right-handed, which means that if I look at along the axis of the helix, and if I would like to move up the helix, I have to rotate like that. If I want to move in that direction, the rotation along the helix, when I look along the axis, it's counterclockwise. So that's right-hand rule. Okay? So this is a right-hand chirality. If it were the other way around, it would be a left-hand chirality. So let's keep the right-hand rule in mind. Okay? I'm going to pull. What's going to happen? So if there is no helix, or if there is a helix, and the Young's moduli are the same, then it's that problem. Okay? But now if I make the Young's moduli different, in particular the helix is much stiffer, then it's not that problem anymore. What's going to happen? What would you expect would happen? Some rotation, and somebody said clockwise. Okay? And so I'm putting the mesh just so that we can see that rotation a little bit easier. So I pull. And the colors are displacement. Blue, displacement in the x direction. Okay? Blue is negative. It means left. Red is positive, right. So it's twist. Okay? So it twisted. So I can also give you, right, a front view just to make it more convincing. And it rotates considerably, right? So u theta is not 0, right? Okay. What if I push instead of pulling? Now, these are things you can build this model yourself and experiment with. I pulled, it rotated. So one has to think about why it rotates, first of all. But suppose I push. Shall I do that for you? So prescribed displacements, let me make it negative. Okay, and I will solve it again. It will take a little bit. I can do several things. Instead of pulling, I can push. Instead of having a right-hand chirality, I can have a left-hand chirality. The Poisson ratio here is 0.3. I can make it minus 0.3. So in other words, when I pull, the material will not try to contract. It will try to expand. Three major variations: chirality, direction of displacement, and the sign of the Poisson ratio. Okay? All of these, it turns out, changes the direction of twist. Okay? So it's a very simple problem with a lot of complications, but I think it makes you think about the underlying mechanics well. But let me just show that to convince you that that's what happens, and then we will move on. Okay, the point here, again, is not the Young's effects or the complication of the solution. The point is that when you build some sort of anisotropy into the material, all of these expectations might directly fail. So we have to be careful. We have to keep in mind what we are assuming. Okay, it's almost done. Okay, so right-hand rule, it was rotating like this, right? And now I am pushing, not pulling. It's rotating the other way around, right? And because I'm pushing, it's contracted, right? And as it contracts, it rotates according to the left-hand rule, let's say. Okay? So let me actually just disable the screen and now move on with the solution of the problem. Solution of the problem, assuming isotropy and based on the omission of the end effects or Seminoles Principle. Okay, so let us start with simplifying my notation a little bit. I'm going to simplify it in the following way. I'm going to call the radial displacement a function capital U. It's a function of r alone. And then there is an axial displacement. I will call it capital W. It's a function of z alone. Okay, so I'm going to work in terms of U and W. And then I go ahead and calculate first the displacement gradient. So as I mentioned last time, I'm going to always remind you from now on only the particular parts that survive based on our simplification. So we've written the full gradient last time. So this time, the only thing that remains, first I will write what remains, and then I will use our notation to plug it into that form. So what remains is this in the gradient in polar coordinates. So UR comma R is simply U prime. And then we have U over R. And then this is simply W prime. Okay? And because it has no off-diagonal components, epsilon, in this case, is equal to H. So this is simultaneously my strain matrix. The volumetric strain, in this case, is not in general 0. So it's equal to U prime plus U over R plus W prime. And the stress is lambda epsilon VI plus 2 mu epsilon. So the stress is equal to lambda times that plus 2 mu times the strain. So I'll simplify on the fly. So lambda multiplies this, but one part of that epsilon d always appears along the diagonal, the first, the second, or the third. So I'll combine those two things into a lambda plus 2 mu. So for instance, sigma RR is equal to lambda plus 2 mu times U prime plus lambda U over R plus W prime. And then sigma theta theta is lambda plus 2 mu U over R plus lambda times U prime plus W prime. And then sigma ZZ is equal to lambda plus 2 mu W prime plus lambda U prime plus U over R. Those are the only non-zero components of the stress. And then we invoke equilibrium, right? So we started with displacement, strain, stress. We close the loop with equilibrium. And equilibrium will eventually help us, together with boundary conditions, help us determine what those unknown functions U and W are. So divergence of sigma, that should be equal to 0. It is a vector. And the only non-zero components that we have to deal with are sigma RR, 1 over R, RR minus theta theta. Sigma, the second component, theta component, is 0. And sigma ZZ with respect to Z, that's the final equilibrium equation. Okay. Okay, sigma RR over R. So U double prime, U prime over R minus U over R squared. Okay, lambda plus 2 mu U double prime plus lambda U prime over R minus U over R squared. And then 1 over R, the difference between these two. So 1 over R, that minus that, that's equivalent to 1 over R 2 mu, this minus that. So plus 2 mu over R u prime minus u over r. 2 mu is over here. That's the R entry. The second entry is 0. And then sigma z, comma z, that's easy. This thing depends on R only, the last entry. The first one is lambda plus 2 mu w, sec 2 derivatives. Right? So sigma rr comma r, that's the first two terms. And then 1 over r, rr minus theta theta, that's the last term. So sigma theta theta only goes into the first equation. And then the last one is this with respect to z. This part is gone. So w double prime lambda plus 2 mu. And both of these are now things that have to be individually 0. Okay? So let us begin with the r component. Okay. So actually it looks much easier than it looks at first sight. So lambda plus 2 mu is a common factor actually, which multiplies u double prime and then lambda plus 2 mu u prime over r over r over r squared over r squared. So actually these two things are similar. So plus u prime over r minus u over r squared is equal to 0. The factor, the material parameters apparently do not influence in this case the value of u. And let me multiply this with a r squared to obtain that expression. Do you remember that equation from last time? Right? It's the same equation actually, it turns out, right? So this is something we're going to encounter quite often. Either we will get, if, for instance, no wonder because the geometries are the same. Okay? So some of the features of the solution depend only on the geometry. You refine it through boundary conditions. Okay? So geometry is the same, and therefore a part of the solution, in this case the radial solution, is actually the same. In this case, it has to do with radial displacement. Previously, it had to do with the tangential displacement. Nevertheless, we got a part that is quite similar. So I know the solution from last time. And I know that the solution is of the form C1R plus C2 over R. And just as in the previous case, we will eventually argue R can go to 0 because that represents the axis of the cylinder. I cannot have a solution that blows up. So the only plausible thing is C1 times R. And let me call for simplicity that constant simply C, not C1. Okay? So then we can go to the second component. The Z component simply says that W double prime should be equal to 0. That is the simplest thing we could possibly hope for. So W is equal to, it's a function of Z, A, Z plus B. Okay? And just like we did in the previous case, at Z equals 0, I don't expect any displacement, and therefore this constant B must vanish. So W is equal to A times Z. Okay? So we therefore have V solution actually with some free constants. And those constants now we need to determine. Let me summarize what we have so far. So we have epsilon RR, right? So now I am going to, sorry for switching, But this is simultaneously equal to epsilon. This is epsilon RR, right? Theta, theta, ZZ. I'm just going to plug in the values. So for instance, epsilon RR is U prime. U is equal to CR, so it's equal to C. Epsilon theta, theta is U over R. Again, it's equal to C. And epsilon ZZ is equal to W prime, which is equal to A. Okay. And based on these, we have the stresses. Sigma RR is equal to, right? And I have the expression for the stresses down there as well. I'll carry on the substitution for you. You can check yourselves. Lambda plus mu times 2 times C plus lambda A. Sigma theta, theta is the same. And sigma ZZ is equal to lambda plus 2 mu A plus 2 lambda C. Okay, straightforward substitution. Do you find it pleasing that sigma RR and theta, theta are the same? Or do you have any idea what actually they should be? So what is sigma RR? It's on the plane with normal R in the direction R. So for instance, on the plane with normal R in the direction R. On that tiny element, that would be sigma RR. So what's sigma RR there? 0. Don't be afraid to say what is obvious, okay? Because it's a part of the solution. If you don't say that, right, then you do not proceed with the solution. So sigma RR is 0. And sigma theta, theta is equal to sigma RR. So sigma theta, theta would be like these stresses that we would encounter. So it's on the plane with, so for instance, if I draw a line here that passes through the radius, on the plane with normal theta in the direction theta. Okay, that would be sigma theta, theta. For instance, if I had a pressure vessel, right, remember, we had tangential stresses that under the pressure try to keep the vessel intact. That's a sigma theta, theta, right? We don't have such a scenario here. So sigma theta, theta should also be equal to 0, but they're equal to each other. So it's easy to see immediately that sigma RR should be equal to 0 on the surface, for instance, because it's a traction-free surface, right? Some things are not explicitly indicated, but it is clearly traction-free, okay? And that enforces RR to 0, 0, and theta, theta is equal to that. So let's make use of that observation. So for instance, right, so this is, I'm picking only a single point, which is the surface, okay, at any axial position. At R equals 0, I have traction-free conditions. Okay, and traction-free, so that says sigma RR is equal to 0. Hence, sigma RR is equal to 2 lambda plus mu C lambda A. And in fact, sigma RR does not depend on R or Z. So as soon as I enforce it to be 0 on the surface, it is automatically 0 everywhere, as I expect. Okay? So this gives me an equation in terms of C and A. So C, if you solve it from that, is equal to minus lambda over 2 lambda mu A. So let's remember ME 101, right? I pull on a rod. The axial strain or longitudinal strain is A. The lateral strain is C. So I pull, it contracts. What is the ratio of C to A? Multiplied by a minus sign, if you like. It should be the Poisson ratio. The ratio of C to A with a minus sign should be the Poisson. So this should be the Poisson ratio. So this is also sometimes a disadvantage of our way of proceeding. Some constants are hidden. But let me remind you with a note. Let's say recall here. Now, there is a, usually in books that are related to this topic, they have nice tables that relate any two choice of elastic constants to any other constant. So, for instance, you can express the bulk modulus in terms of Poisson ratio and Lamé parameter lambda. Or, for instance, you can express, and this we know, the shear modulus in terms of the Young's modulus and Poisson ratio. And similarly, you can express lambda in terms of the Young's modulus and Poisson ratio as well. Okay, so this one I had not written before. This is new for you. But I'm writing it so that you can go ahead and check yourselves. So from this, you can eventually find that lambda over 2 lambda plus mu, which is exactly this quantity, is equal to the Poisson ratio. Okay? Just plug in these two into that expression. So this, here it's mu, and therefore we have C is equal to minus, it's nu. So C is equal to minus nu A. And therefore we have, for instance, epsilon RR over epsilon ZZ, or epsilon theta theta over epsilon ZZ with a minus sign is equal to the Poisson ratio as we expect. Okay. So I'm almost done with the solution. Let me finish this example. Let's erase this. Any questions, by the way? Okay, so I got a relation between C and A, and now I will go to sigma ZZ. So now sigma R and theta theta are both 0. That's the condition I imposed to find out this relation between A and C. So now, however, I still have one constant unknown. Let's say A is still unknown. If I know A, then I know C. So that I need to still find out. So now let's go back to sigma ZZ. And let's observe that it takes the value lambda plus 2 mu A plus 2 lambda C, right? But C is now something that I already know. It is lambda nu, right? Or if you like, I can plunk this quantity. Minus 2 lambda squared over 2 lambda plus mu. A. And the 2's cancel. Okay. You just have to do some multiplication with a common denominator. So if you do that, you get 3 mu lambda plus 2 mu squared minus lambda squared, right? So all I'm doing is I multiply that part with lambda plus nu, collect everything, and now lambda squares cancel each other, and I am left with mu times 3 lambda plus 2 mu over lambda plus mu times A. Okay, so now again, I have an expression for mu in terms of E and nu, and for lambda as well in terms of E and nu. If you take these and plug them in there, okay, then you will find that this is exactly equal to E. Okay. So sigma ZZ is EA, and no wonder. A is the axial strain, epsilon ZZ, so sigma ZZ is strain times Young's modulus. Okay. And so the only question remaining is what is A? And I have two conditions, right? So I could have either a end displacement. So the argument is sort of following what we did for the case of torque. I could have a end twist or a end torque. So in this case, we have an end displacement or a end force, P. And in the case of the end displacement, so what that tells us is that W UZ is a function of Z alone, and that's equal to AZ by our construction, right? And so now at Z equals L, UZ is equal to delta. That's our condition. But simultaneously, I could go into this function and plug in Z equals L. It should be equal to A times L. And there is my condition for solving for A, which is delta over L. Okay? Displacement per unit length, or what we called earlier in our ME 101 course, let's say, the average normal strain. Okay, so that's easy. So that would be our longitudinal strain or axial strain. Let's look at the second case. Now, in the second case, what we have to do is invoke an argument. Again, and I just want to emphasize this once again. There is a force at the end of the cylinder, right? I'm pulling on the cylinder is constrained on one end. There is a certain stress distribution at this end that causes this particular force. Okay? You cannot impose a force in practice at a single point. And if you do that, in fact, there will be strong end effects because the stress is not uniformly distributed at the end. So if we impose it at the end, we had discussed this before. If I indeed impose the force at a point, then there will be a very pointed displacement where I apply the force, right? Obviously, there would be an end effect. That could be how I'm applying the force on a very, very small area. And eventually, the argument is I don't care how I apply the force. If I'm sufficiently far away from this end where such end effects dominate, they probably decay exponentially anyway to some situation where, for me, what is really important is that I have static equivalence. That's what I care about. So again, the underlying idea is we omit end effects or we invoke Seminoles Principle. So if I integrate sigma ZZ over the area, then I should obtain the force that is being applied. Sigma ZZ is nothing but E times A, right? Right there, E times A. And therefore, this is E times A times pi c squared. Let's call that the area of the cross section. So A is equal to P over E. Now, given this force, you might also be willing to calculate the displacement of the end in an average manner, again, invoking the Seminoles Principle. So delta is A times L. and that is PL over EA. Again, delta is PL over EA is an equation that we learned a very long time ago. We're verifying it, and again, we had a chance to discuss many different aspects of the solution. Okay, so this is, I think, very good warm-up. We are essentially done with these two good warm-up examples. And starting next time, what we're going to do is we're going to start attacking problems that we could not solve before in our earlier courses. Okay? And the methodologies that we use will, again, be similar. Okay? So I'll see you next time. The quiz var haftaya, unutmayın.